learn more about complex composition theory, and we'll learn it from Zhipeng. Zhipeng Duan is from Nanjing Normal University.
Okay, thank you very much for Guchuan for introducing me, and thank you very much for organizers to invite me to give 2 talks in this summer school about chromatic stuff. So today my talk is about the calculations of a generalized homology on complex co-Bordizan spectrum MU, and try to explain the spectrum MU is a universal complex-oriented co-homology theory. So here COCT is just a shorthand for complex-oriented co-homology theory. So my talk will separate into the following 3 parts. So we'll first try to calculate the generalized homology and co-homology of a classifying space BU. And the main result is just the generalized homology E star BU is a polynomial ring on coefficient E star on generators beta 1, beta 2, and so on. They are infinity generators. And the co-homology, the generalized co-homology BU is E star is a power series, and is on generators C1, C2, C3. There's also infinite generators, and here the generalized the spectrum E should be complex-oriented co-homology theory. And the second part I will give, as you see in last lecture by Yutao, he showed 2 definitions of complex-oriented co-homology theory. And I will give a short proof, so why these 2 definitions are equivalent. And then based on this equivalent notions, I will show that the generalized E homology of MU is just isomorphic to E homology of BU when E is a complex-oriented. So just E star of MU is isomorphic to E star on B1, B2. It's also infinity generators. And the last part, I will use this calculation result to explain why the complex co-Bordizan spectrum MU is a universal complex-oriented co-homology theory. And this is just a 1-hour talk, so I cannot cover all details. So I will try to highlight the main ideas behind those results and calculations. And if you are interested to read more details, and I list several related sources, which I learned a lot from them. So I also texted these sources in chat channel. So the first source is Coachman's book, is titled Bordizan, Stable Homotopy and Adams Spectral Sequences. And the second source is Adams' classical blue book. It's called Stable Homotopy and Generalized Homology. Although it was written 40 years ago, but still contains a lot of interesting, fruitful mathematical materials. So it's highly recommended to read it. And the third source I recommend is Rory's lecture notes, and you can find it on his website. And the fourth source is Swiss's classic book, is about algebra topology, homotopy, and homology. So let's get started. So the first part, I will try to calculate the generalized homology of BU and co-homology of BU. And for when E is a complex-oriented co-homology theory. So here is again complex-oriented co-homology theory. So in order to do these calculations, I will first try to recall several classical results. So the first result I want to recall is about the singular co-homology and the singular homology calculation result is a H star of BU and H high star of BU. And here in this talk, H star is just means the singular homology with C coefficient, and it's similar for singular co-homology. And in following, I list several results relevant to the single homology co-homology of BU, which will be used later. And all of these results you can find in Coachman's book in section 2.3, because I will just state its result and say a little bit about the idea behind it. But if you are interested about details, you can just check this in Coachman's book. Okay, so the first result is about the co-homology of the classifying space of a unitary group UN. So this just says the co-homology BUN is a polynomial ring on Z coefficient with n generators C1, C12 to Cn, and the degree of Ci is just 2i. And this generator set name, the Ci is I's Chern class. So it's I's Chern class. And about neutrality, so if there are two natural numbers, m is less than n, so we have a natural map from the classifying space BUM to classifying space BUM. And in co-homology level, if we apply co-homology functor, there is a map from co-homology BUN to co-homology of BUM. And it turns out this map is a surjective map. And moreover, it will map the generator Ci in the left-hand side to the generator Ci in the right-hand side if I is less or equal to m. And otherwise, if I is greater than m, then Ci will be mapped to 0. And then the associated to the classifying space is a tautological bundle. And in last Utah's talk, he defined what is the tautological bundle. So there are two tautological bundles, gamma m and gamma n, over BUM and BUM. If you consider the direct sum of these two tautological bundles, then you have a dimensional m plus n bundle over the space BUM cross BUM. Then by classification theorem, there is a classifying map from BUM cross BUM to the classifying space BUM plus n. Then on the co-homology level, this map will induce co-homology of BUM plus n to co-homology of BUM tensor co-homology of BUM. Then under this map, the top Chern class in right-hand side, Cm plus n, it will map to the top Chern class Cm in co-homology of BUM tensor with top Chern class Cn in co-homology of BUM. And the idea behind this, the correspondence of these two Chern classes is as follows. So if you consider the direct sum of line bundles, so if you consider n copies of line bundles, here consider n copies gamma 1, and this also n copies tautological line bundles of BU1, and you consider direct sum of these line bundles. Then similarly, this will form an n-dimensional bundle. Then by classification theorem, we have a classifying map from n products of BU1 to BUN. So this is also a classifying map. Then if you apply co-homology functor, we have co-homology of BUN to co-homology of n product of BU1. And by Coachman's theorem, the co-homology of n product of BU1 is just isomorphic to tensor product for n copies of the co-homology of BU1. And furthermore, the direct sum of line bundles is invariant up to isomorphism under actions of symmetric group. So if you change the order of direct sum by the action of symmetric groups, but up to isomorphic is just equivalent. So it reflects on co-homological level. So this map will factor through. You have factor through the invariance of the tensor product of n copies of co-homology of BU1 under action of the symmetric group sigma n. And moreover, this factorization turns out to be equivalent isomorphism. And under this isomorphism, the generator Ci, the ith Chern class, it will be mapped to the ith symmetric polynomial. in this invariance. So this will generalize to the above result. In general case, the top chain class Cm plus n will map to the Cm tensor Cm. And then the first three results is about the co-homology of classifying space. And then the next result is about the homology one. So the homology of yes, it's an elementary symmetric polynomial, yes. And the homology of classifying space, it turns out to be a free Z module on monomials beta I1 times beta I2 up to beta IN. So what is this beta class? You see, if you calculate the basic case, so the homology of CP infinity is just a homology of BU1. So the homology of CP infinity is isomorphic to free Z module on generators. If you write the generators as 1, beta 2, and so on. And you can also denote the 1 as beta 0. Now these monomials, the beta I1, beta I2 just comes from those beta class. And of course, there's a relation, there is a map connecting the co-homology and homology of a classifying space by the universal coefficient theory. So here, the universal coefficient theory actually in this case gives the following isomorphism. So the co-homology of BUN is isomorphic to the home from the homology of BUN to Z coefficient. And moreover, under this isomorphism, the generator Ci, it actually maps to the dual vector of beta 1 to the I. So the dual vector is a homomorphism. So this dual vector is a homomorphism from the singular homology of BUN to Z, and it maps to the beta 1 to I to 1 and other generators to 0. So this is the several results we need later and about the homology and the co-homology of BUN. And then you can pass to co-limits. So you can pass to stable a classifying space BU. So for example, as a homology, because the homology commutes with the co-limits is just the homology BU is just the polynomial ring on generators beta 1, beta 2, and so on. And the degree of beta I is just 2i. And as for co-homology of the stable classifying space, and in general case, it has a lim1 term. But in this case, the lim1 term vanishes. So here the lim1 term is 0. And this is just because the inverse system, according to the previous result, from co-homology BUN maps to the co-homology of BU-1. This just the surjective. And so it satisfies the Mittag-Leffler condition, and it just means the lim1 term in this case is trivial. And it implies the co-homology of BU is a polynomial ring on Z coefficients with generator C1, C2, and so on. And the degree of Ci is just 2i. And moreover, this corollary express these two homology or co-homology as with algebra structure, but actually it is a hopeful algebra. So this is a remark. So this is both are hopeful algebras. And with the coproduct structure, it just looks similarly. So phi Cn is a summation from k from 0 to n, Ck tensor Cn minus k, and the coproduct on beta n is a summation k from 0 to n beta k tensor beta n minus k. But I mean, this hopeful algebra is actually not relevant in this talk. What we need is this algebra structure. Okay, so this is this is the first. So what I said above is a calculation result, the classical calculation result of the singular homology and co-homology on classifying space and the stable classifying space. And in order to do the calculations on generalized homology and co-homology, we need a second result. And in previous talk, we defined the co-homological version of Hertzberg spectral sequence, and there's also a version of a homological Hertzberg spectral sequence. So let E be a ring spectrum, and X be a finite CW complex. Then we have the following two spectral sequences: homological Hertzberg spectral sequence and the co-homological Hertzberg spectral sequence. And moreover, between these two spectral sequences, there is a natural map called pairing. So this pairing is from E2 page, and it is induced to each next page. So in each page, there's a pairing from the homological Hertzberg spectral sequence tensor with the co-homological Hertzberg spectral sequence maps to the coefficients. And this pairing actually satisfies the following basic properties. The first property is on E2 page, this pairing coincides with the usual pairing on singular homology and singular co-homology. So what does this mean? So on E2 page, there is the pairing just looks like you have nth co-homology with, coefficients G, also with nth homology with general coefficient G prime, and it will map to G tensor G prime. This is just defined by evaluation. So evaluation of trend on co-chains. And the pairing here on E2 page just coincide with the usual pairing on singular homology and co-homology. And the second property is about a kind of a duality between differentials. So there's a duality. So if you have differentials on homology common with a class on co-homology, then it just equals to the pairing on class X, and you apply the differential in co-homological Hertzberg spectral sequence on the class Y. And it just tell you if you know some information about differentials on homological or co-homological Hertzberg spectral sequence, then you can use this pairing to know some information about the differentials on other ones. And the third property is just tells you that this pairing on spectral sequence is natural. It's because we also have pairing on convergent term. So we have defined pairing on E star, E co-homology X tensor E homology X, and this pairing will induce the pairing we have on the infinity page. So what is the pairing on generalized co-homology homology? So you just define like this. So you have En X tensor Em X, and it maps to Em minus N, the coefficient Em minus N. So you have two class F and comma G. And then the pairing just defined as a composition of the following maps. So if you start with the class G, you have a map from the M sphere to E smash X. Then you apply the class F, it maps to X to the N suspension of E. So it maps E smash N suspension of E. And because E is a ring spectrum, you have a multiplication, so it just maps to N suspension of E. The other composition is just the pairing F comma G in generalized homology and co-homology. And actually, there is still several technical issue about convergence in Hertzberg spectral sequence. And in fact, I omit one technical condition for convergence is I just ask the complex X to be finite. But actually, for convergence in homological Hertzberg spectral sequence, we actually need the spectrum E to be bounded below. And the following I will prove several results using the pairing between the homological and the co-homological Hertzberg spectral sequence. And my argument actually works for the case bounded below spectrum. But actually the result I proved still works in general case. So Rory, in his lecture notes, lecture 4, he used a technical trick to get rid of the assumption about bounded below. So this is for our purpose. This assumption is actually unnecessary. So if you are interested, you are recommended to read Rory's notes. Okay, so let's try to see how do we apply the pairings to get our calculation result. So as a warming up, we first calculate the generalized homology of BU1 is just the CP infinity, given E is a complex oriented spectrum. So just so the main idea is apply the T-Hispo spectral sequence. But because we try to use the pairing, so we need to assume the complex in the T-Hispo spectral sequence should be finite in co-homological version. So we first try to calculate the generalized homology of CPM. So this is the E2 page of the T-Hispo spectral sequence homological version. Then we also list here the co-homological version. So it will converge to generalize the co-homology of CPM. And according to last talk, we already knew the co-homological T-Hispo spectral sequence already collapses on E2 page. So the duality ring pairing will show that the homological one actually also collapses at E2 page. So this just means the generalized homology of CPN is actually isomorphic to the homology, the single homology of CPN tensor product with the coefficient E star. So in other words, the generalized homology of CP infinity is a free E star module on generators 1, beta 1, beta 2, and so on. And with the degree of beta I just 2i. And here E is complex oriented. Okay, so this is a warming up as a basic example. So the following is the theorem is our main theorem of this section. So if E is a complex oriented spectrum, then its homology, the E star of the classifying space BUN, is actually a free E star module on monomials beta 1, beta I1 times beta I2 up to beta IN. And you see this is very similar like the classical calculation of the singular homology on BUN. This is just because you just replace the C coefficients by the general E star coefficient. And similarly, as for the co-homology, then the E star of the BUN is similar like the singular co-homology is a power series on E star with generators C1, C2 up to Cn. And actually, there's also the universal coefficients theorem also gives the following isomorphism from the generalized co-homology of BUN to home from the generalized homology of BUN to coefficient E star. And under this isomorphism, the class Ci, it will be mapped to the dual vector of beta 1 to the I. And also, this class is called the generalized Chen class because it enjoys the similar properties as the Chen class in singular co-homology. And we also called in some literature called the Kroner-Floyd Chen class. So next result is just the similar properties we list above about the singular co-homology BUN. It still works, still holds on the generalized co-homology of BUN. For example, the co-homology BUN to co-homology of BUN-1 induced by the inclusion map from BUN-1 to BUN. It will act if surjective maps and actually maps the generators to Cn if I is n is Ci if I less or equal to n minus 1, that's 0 if I is equal to n. So I will give a sketch proof of this result, and you see this the result is very similar to the calculation on singular homology and co-homology, and this is just simply because the related artificial spectral sequence on homological one or co-homological one both collapses at the E2 page. So first, as for the homological artificial spectral sequence, so this is the homological artificial spectral sequence for BUN. And we claim this spectral sequence collapses on E2 page. So how to see that? So again, let's consider the classifying maps to the classifying maps to classify the direct sum of n copies of line bundles. It's just n copies of BU1 maps to the classifying space of UN. Then this natural map, the topological map, will induce a natural map between spectral sequences. So this is the left-hand side is artificial spectral sequence. Calculate the E-homology of n copies of BU1. And this is right-hand side is our artificial spectral sequence to calculate the E-homology of BUN. And this is the natural map between these two spectral sequences. And as you see, by Kuhn's theorem, this is just the tensor product for n copies of BU1 and tensor with E star. And this is just the homology of BUN tensor with E star. It's just because the homology is free. And then it's also a map. Then we know the classes here, according to the previous result, the class here is the generator is a monomial, beta I1 times beta I2 times beta IN. And this monomial actually comes from the left-hand side is beta I1 comma beta I2, or maybe tensor up to beta IN. And according to our warming up example, so in homological artificial spectral sequence to calculate BU1, those classes are permanent cycle because the artificial spectral sequence collapse at E2 page. So those classes are permanent cycles. Then the tensor product is also a permanent cycle. Then this naturality will forces the generators here, these monomials, are also permanent cycles. So it just proved this spectral sequence collapse at E2 page. So then because this spectral sequence collapse at E2 page, then the generalized homology of BUN is just isomorphic to the homology of BUN tensor with the coefficient E star. So just in other words, it's a free E star module on those monomials. So what about the co-homological version? And you see the co-homological artificial spectral sequence, we need ask the complex to be finite. So we first try to filter the classifying space BUN by its skeleton. So we consider a subcomplex of BUN with dimension less or equal to Q. So this is a finite subcomplex. We first try to calculate the generalized co-homology of this complex. And we know in this case, we apply the artificial spectral sequence in co-homological version. Then we also claim this artificial spectral sequence collapses on E2 page. So why is that? So now we need to use our pairing. So we also consider the homological artificial spectral sequence on this finite subcomplex. And you know the artificial spectral sequence, the homological version is a sub-spectral sequence of what we just calculated here. So it implies this homological version. So this spectral sequence also collapses at the E2 page. So it collapses on E2 page. So then, similarly, using the pairing argument, this collapseness on E2 page of a homological version will imply in co-homological artificial spectral sequence also collapse at the E2 page. This just means the cohomology of the finite complex is isomorphic to the singular cohomology tensor with the coefficient. Then again, if you pass to the stable classifying spaces, then you get and you easy to see the filter the subcomplex case here. The on cohomology, this is also inverse system. So you pass to the generalized cohomology of BU. General cohomology pass to, sorry, this is a typo. Pass to BUN. So this is the power series on E star, the coefficient E star with n generators C1, C2 up to Cn. But here I want to remark, so those generators in E star BUN, C1, C2, Cn, this actually depends on the choice. So those generators depends on the choice of the complex orientation of E. Because you know the C1 is just the E cohomology of BU1 is E cohomology CP infinity is just the complex orientation. And the choice of C2, C3, and Cn, this is higher chain class, is actually determined by the first chain class C1. And the determination you see is just because the ith chain class is actually the ith elementary symmetric polynomial on n generators, and those generators are all complex orientation. Okay, so then as a corollary, so if E is a complex oriented cohomology theory, then the E homology of BU is just isomorphic to E star on those generators beta 1, beta 2, and so on, infinite generators with degree of beta is 2i. And the cohomology of BU is a power series with E star coefficient on infinite generators C1, C2, and so on. And the generators of Ci are also 2i. The degree of Ci are also 2i. And this is the first part. So this part is maybe it's mainly about the calculations. So it's a little bit technical. So, but for the next two parts, we will apply the calculation result to see some conceptual things. So in the second part, so the title is a complex orientation revisit and the generalized homology of a complex cobordism spectrum MU. So I just the first result is about the equivalence of the following two statements. The first statement is a complex oriented ring spectrum. So I'm very sorry. The definition I use about complex oriented is actually the second definition in Yutau's talk. So this just means, so there is a class in E2 CP infinity, and it will maps to the unit in E2 of S2. So I mean, this is my definition for complex oriented ring spectrum. And the second one is actually Yutau's definition. Is actually each complex bundle is E oriented. So why these two definitions actually equivalent? So before we prove, I need to a short review what does mean of E orientation of complex bundles. Just you have natural assignment of class in Tom space, the Tom class. So if V maps X is a bundle, so if you can find a Tom class, the restrict to fiber, the unit, and satisfies like the pullbackness and the Drexel action, then it is called the E orientation. So why it is equivalent? So we have two directions. So the one direction is a relative easy. Is from the statement 2 to statement 1. So if we assume that each complex bundle is E oriented, how do we show that the spectrum E is complex oriented? I mean, actually, we just need to find the Tom, just to find the complex spectrum, the ring spectrum E satisfy this property. So because each bundle is E-oriented, so in particular, the tautological line bundle, the tautological line bundle is E-oriented. So by definition of E-oriented, so you can find a class, the Tom class U gamma 1 is restricted to a unit in a fiber, the E2 of S2. And you know, this is exactly the definition. So my definition for E is a complex oriented ring spectrum. So I mean, this direction is a little bit easier. And as for the converse, so if you assume the spectrum E is complex oriented, how do we show that each spectrum, each complex bundle is E-oriented? So I mean, because of the classification theorem, so we actually sufficient to show that each tautological bundle is E-oriented. So in other words, we need to find the Tom class in each tautological bundle. So this is the tautological N bundle. So how do we do that? So again, we consider the classifying map. So this is the classifying map about the direction of N copies of line bundles. So then we have this pullback diagram. And if we apply the Tom space functor, then we have a topological map from the N slash products of the Tom space of gamma 1. This is just MU1 mesh up to MU1. And this is MUN. So we want to apply this map to find the Tom class of MUN in help of the complex orientation on MU1. So how do we do that? So first I state a fact about the co-homology, the generalized co-homology of MUN. So this is says that the E co-homology of MUN is just the power series on one generated UN with E star coefficient. So how to see that? So this is simply because we have simple geometric fact that the Tom space MUN is actually homotopy equivalent to the quotient of the classifying space BUN by the classifying space BUN-1. So why is that? So this is just by definition of the Tom space. So in Tom space, it's defined by the quotient of the disk bundle by sphere bundle. So what is the disk bundle here? So here the disk bundle is just the total space is EUN cross UN on D2N. And this is just homotopy equivalent to EUN quotient UN. And this is a model of BUN. And as for the sphere bundle, so this is just the EUN cross UN of S2n-1. This is equivalent to EUN quotient, the stabilizer, the UN on action of the sphere S2n-1 is UN-1. And this is the model for the classifying space on UN-1. So then you just see the geometric fact. Then you find this homotopy equivalence, then the long exact sequence just implies the co-homology on BUN is just the power series of on CN on E star coefficient. Then we apply the generalized co-homology functor on this map. In other words, we have the natural map from E star, E co-homology MUN to the N tensor product of E co-homology on MU1. And as you see, the CN, it maps to the trend class, because the E star MU1 just have first trend class. Is also the complex orientation we choose. Is a tensor product of XE, the N copies of XE. And by definition, this complex orientation will restrict on fiber to unit. So this will restrict to unit. Then by naturality, CN will also restrict unit. So in other words, Cn is satisfied is a Tom class. So then the tautological n bundle is E oriented. So this is the short proof about why the two definitions of complex orientation are actually equivalent. So moreover, as you see, if you have Tom class, you have an oriented bundle, then you have the following, the Tom isomorphism. So just like the singular homology case, so if you give an n-dimensional bundle, V2x is E oriented, then we have the following homological Tom isomorphism. If you have homology, E homology of Tom space to the E homology of a base space X, and actually the proof is actually similar to the proof in singular case. So as a corollary, in our case, because the tautological bundle is E oriented, so we have the following isomorphism from the E homology E star plus 2n of MUN to E star of BUN. And actually, we can move the degree 2n inside. So if we can rewrite this as E star of 2n desuspension of MUN, and this is equivalent to E star of BUN. And the complex cobordism spectrum MU is actually homotopy is equivalent to homotopy co-limits of the suspension spectrum of the 2n desuspension of MUN. And here the stable class-fine space is a co-limit of BUN. So then each level Tom class will gives isomorphism on spectrum level. So we have E star of MU, which is isomorphic to E star of BU. But the Tom isomorphism in general is a group isomorphism. But in spectrum level, in this case, we can say more. So actually, so there is a ring isomorphism from the E star of MU to E star of BU. So in other words, the E star of MU is actually you can write the E star of MU in exactly similar term as E star of BU. So it's a polynomial on infinite generators. We denote here B1, B2, and so on with coefficient E star. And under this ring isomorphism, the BI will correspond to beta I, which is generated on E star of BU. And if you're interested why this is a ring isomorphism, you can check the details in Sweden's book, the chapter 16, for details. And moreover, I give a second remark here is we know from the last talk the complex cobordism spectrum MU itself is complex oriented. So MU is complex oriented. So actually, we calculate as a specific example, MU star MU, you can write it as MU star of B1, B2, and so on. So this is expression of MU star MU, and actually, as a fact, so I don't have time to prove here, but this is just a fact that MU star common with MU star MU is a hopeful algebra. Okay, so this is the second part. The final part, I will try to explain to you why the complex cobordism as a complex orientation, complex oriented cohomology theory is a universal complex oriented cohomology theory. So this is basically the following correspondence. So we say the set of ring maps from the complex cobordism MU to ring spectrum E is just a one-one correspondence to set of complex orientations on the ring spectrum E. So why is that? So I give a sketch proof by trying to construct the bijective maps, the two maps on two directions which are inverse to each other. So the first direction map is phi. It's from the set of ring maps to the set of complex orientations on it. So it will assign a ring map FMU to E to the push forward F star of XMU. You apply this ring map to push forward the complex orientation on MU to give a class on E co-homology of CP infinity, and we claim this class is actually a complex orientation. So why is that? So we consider the following diagram. So we have the E2, the MU2 of CP infinity, and by a natural map F star, it maps E2 of CP infinity, and we have a restriction map on left-hand side and the restriction map on the right-hand side. And we have the commutative diagram, and there is a complex orientation we denote by MU, and it will by assumption it will map to unit 1. And this is the map is a ring map, so on the algebra level, the map will also map, the unit will also map to unit 1. And here in the top level, the class XMU will map to F star XMU. So then by neutrality, by commutativity, so this class, the restriction must also be forced to the unit. So it just means that the class we define F star MU, XMU is actually a complex orientation on U. So this is actually one direction of this map. So what about the inverse direction? So inverse direction, we need to try to construct a map from the set of complex orientations on E to the set of ring maps from complex copolysis MU to E. So in other words, we need to assign each complex orientation to a ring map from MU to E. So how to construct this ring map? So we recall for each singular co-homology, so each generalized co-homology, E star of MUN. This is actually equivalent, it's actually isomorphic to the power series on single one generator Cn. And this Cn in this co-homology is actually corresponds to this map. It's from MUN to E2N. So on point set level, those chain class C0, C1, C2, up Cn, and so on point set level, the collections of this map, we claim it will give a ring map from MU to E as we want. So how to show that? So we need first try to show the collection of this map is actually a map between spectra. Then we need also argue that this map is actually ring map. So why it is actual a map between spectra, we need to track first two properties. First is about unity. We need to show that the map we constructed is commutative up to homotopy from these two unit maps, the unit map from sphere spectrum. And on point set level, it's just equivalent to the commutativity up to homotopy of this triangle. And these both maps are actually the unit map. And the vertical map is a class Cn. So why this map is commutative up to homotopy? It's just because the class Cn is Tom class. And the commutativity of this diagram just means the restriction of the class Cn on fiber is a unit. So this is okay because Cn is a Tom class. So then we need to show the collection of our maps actually compatible with the structure maps inside the spectrum. So in other words, we need to show that this diagram actually commutes up to homotopy. So how to show that? So we first consider the simple case when n is 0. Then the diagram degenerates to this triangle diagram. A triangle diagram, this map C1 is actually the first chain class is actually the complex orientation on E. It's a complex orientation X on E. And then this diagram commutes is just simply because the definition of complex composite, and because the MU1 is CP infinity. So this also commutes. And then for general case, let's consider the following diagram. So our diagram here is actually a composite of these two diagrams. And this diagram is actually the triangle diagram smashed with the Tom class CN. So actually the top square actually commutes out homotopy. And the bottom square, the middle map is C1 smash CN, and the bottom map is Tom class CN plus 1. And why the bottom square commutes? You can see if you go along this way, the composition of this map just corresponds to the class C1 tensor Cn in generalized homology of MU1 tensor the generalized homology of MUN. And if you go along this way, then this will correspond the class Cn plus 1 in generalized co-homology of MUN plus 1. Then the commutativity is just corresponds to the red map in co-homological level will send the Chern class to a tensor product, the Cn plus 1 map to Cn tensor C1 tensor Cn, and this is the basic property we listed in the beginning. So actually this diagram also commutes. So we have shown that the collection of the maps on point side level actually give rise a map between spectrum from MU to E. And similarly, why it is an actual ring map on point side level, we just need to track that this map is also, this square also commutes up to homotopy. And similarly, if you go along this way, this map corresponds to a class, the Cn tensor product Cm tensor product with Cn inside the generalized co-homology of MUM tensor with the generalized co-homology of MUN. And if you go along this way, then it's just Cm plus n is in the generalized co-homology of MU n plus n. And the commutativity of this map is just guaranteed by the red map on co-homology level. It will map the Chern class Cm plus n to a tensor product of Chern class Cm and the Cn. So we actually proved that we actually constructed the map, the inverse map. And actually you can track that these two maps are actually inverse to each other. And the reason, because this is just the fact I said before, like the higher Chern class is actually determined by the first Chern class. And then the first Chern class is actually the complex orientation we choose. So this is why the two maps are inverse to each other. So this is the short proof to say why MU is a universal complex oriented spectrum in this sense. But in the end, I want to say a bit more. So actually, there's some more universality about the complex co-Boson spectrum MU. So in last talk, you shows that for each complex orientation, each complex oriented spectrum with a chosen complex orientation, it gives rise to a formal group law. So in this case, for complex co-Boson spectrum, we also have a formal group law FMU. And this is actually universal one in the sense of formal group law. And more precisely, if we're given any formal group law F over a graded ring R star, then we can find a unique ring map from MU star to R star such that this map will push forward the formal group law on MU to the formal group law over R star. And actually, this is a big theorem by Quillen, and you will see more discussions about this universality and also about the Hopper algebra MU star MU our next two talk tomorrow by Guchuan. And so this is the end of my talk today, and thank you very much for all listening.